How are you? Okay.
I'm done.
All right. Okay. So good afternoon again. And today's lecture, we're gonna just learn about one important topic called map projection. And map projection is very important because the data that we have or anything that we are doing on the earth, there's one thing that we should never be, deceived about. We should never forget that the earth is a round object. Okay, so the earth is round, and I know this one. There was a time where people did even argued and fought over it. The world is round. Some will say it's flat, and then they will kill you. Are you okay? That's how bad it was. But as engineers and as people who work with data and then solution providers and everything, we're supposed to understand that when you work with data that is actually on a flat object, let me just say, when you have data on a flat sheet of paper, you should know one thing, that there's something not right. And so don't deceive yourself. In other words, when you work with projects that will span between, say, Togo and Ghana, you start having issues. And you may never know why, simply because then the curvature of the earth is coming in. In other words, you align it to yourself by actually putting everything on a flat sheet of paper or maybe on a flat screen. So it brings us to a very important concept called map projection. Okay, now you see georeferencing there, but later I'll touch on that, because georeferencing links up with map projection in the sense that we're trying to actually project our data mathematically, okay, from a round surface to a flat surface. Okay, because already the earth is round. And so if you draw a plan, let me say, of a building or of any structure, and then you put it flat on a sheet of paper, someone can really challenge you and say, hey, it's supposed to be bent. Really, technically speaking, it's actually bending because the earth is round. That's the very fact, and the justification for this topic is that everything that we're doing on the surface of the earth, we're doing it on top of something that is round and spherical and not something that is flat. And so there's supposed to be, if you like, some correction, if possible, to be applied to it. And so map projections, that's what it's all about. But how can we talk about map projection? We don't know even what a map is. But obviously, a map is a representation of geographic reality. Okay, I mean, I won't ask you to define it, but everyone needs to know that you need to move from one place to the other, and you make use of a map simply because the map then becomes a representation of everything around you. Okay, so that you can now know that, okay, behind me I have a river body, ahead of me I have a school or this facility or that facility. Are you with me? So maps are really everything that we are doing on the surface of the earth. It represents them, everything that you see on the surface of the earth. So as engineers, where do you work? You don't work in a vacuum. You don't actually work in space in somewhere. You work in the built environment. Okay, and engineers don't work everywhere. Sometimes an engineer is just seated in some one office, but he's working, he's solving the problem. He doesn't have to, he may visit a location just to confirm. Okay, but at the end of the day, you're working with plans and maps, which are just, reduced versions of the actual ground reality, the actual reality, the actual reality. All right, so let's look at a few things about maps. Then we will get closer to, map projections. Okay, one of the things about maps that you need to know is the scale of it, the scale of a map. Okay, you must just know. That's what I've written there. Must know the scale of a map. Okay, and we saying that it's a method for expressing how a map distance compares to the ground distance or distance on the surface of the earth. In other words, everything that you see on the map, which is really like, you see, on a map can be on a paper or it can be on a computer. Are you all right? Until you print it out, it's still a map. It's some kind of virtual map. You can't touch it. But then what they've known over the years is a paper map. Are you okay? All right. So the map scale then is a value. Are you okay? You know, you can call it saying a method, but really it's a value that allows us to relate what is actually on the ground to what is on the paper map or on the map. Are you okay? So there's a formula. So what you are looking at here is a formula that wasn't well written because this was generated with PowerPoint. Distance on a map divided by distance on the ground. Are you okay? That is what map scale is. So it's really a ratio. Are you okay? So at the end of the day, we have different types of map scale. We can have what we call the graphic scale, which is what you are looking at now. So in this case, graphically, we want to describe what the distance is on the ground. So typically, when you are looking at the scale bar, you will see that it's actually drawn on the map, which is the representation of what is happening on the ground. And then we should be able to look at it and then say that, oh, okay, if I actually move from here to here on this small space, so on my phone right now, on your screens right now, if you actually look at it from the very beginning of the bar to the end is 440 meters, which is not true, right? Exactly. But then we are trying to say that everything represented on that map, then this bar is trying to give you an idea how the distances are on the ground. Now, when you look below the bar, you also see one, and then there's a column 2,500. 1 is to 2,500. Okay, every engineer needs to appreciate scale, and these are the two scales. You can have also what we call the verbal scale. So this one here is actually the representative fraction scale, which is very popular among engineers. 1 is to 2,500. Most buildings, front elevation, plan and all that can be, depending on what it is, 1 in 50, 1 in 100. If it's an engineering drawing, it's not that, not a small scale, it's rather a large scale. Okay, so we need to also appreciate what is large and what is small in terms of scale. Are you okay? Because obviously what the scale is the scale is only helping us to reduce the distances which are actually on the ground so that we can relate with it in the office, or in our model. Okay, so when you look at these values here, large scale versus small scale, you can see that 1 in 2,500 is larger than 1 in 200,000. Someone got confused, right? And they're like, what are you talking about? But I know all of you are okay. If you're not okay, let me know. You can call me and I'll explain to you. you don't need to let your friends know. But virtually 1 in 2,500 is larger than 1 in 200,000. You can also ask a question in this class if you feel you are confused. But here, what are we saying? Large scale means that objects can easily be distinguished as if the objects are large, but really that's not what we are saying. Okay, the sea is large, where we can kind of reduce it. In a small scale, it's easy to represent the sea on a small scale than to represent it, on a large scale map. Okay, so the word large gets a bit confusing. Is it the object that's large? Is it the ground that's large? That is where. So, but put in your mind that it's a ratio, and if more, less divide. If you attended a private international school in Ghana, then you are taught those things. But if you attended a government and public school, you don't get to know that. If it's large, then you have the denominator being small. If it is small, then you have the denominator being large. So that's how one way of determining if a scale is large or small. So here, large and small are being compared. These are things you need to know in maps, okay? In that representation. So what you are seeing now is just the Earth on the left-hand side, a 2D representation of a 3D object round. And then on the right-hand side, you see the map. So there's a direct relationship between a map and then the ground, the Earth. Are you okay? So now the concept of map projection. The concept of map projection. Are you okay? Now we need to do what we call projection. Why? Why are we trying to project? Are you okay? We're trying to reproject because of the coordinate system. You can never talk about map projection without talking about coordinate systems. On the round Earth, the best coordinate system we've seen is the longitude and latitude. And then on the flat sheet of paper, you don't talk about longitude and latitude. You rather start talking about the grid coordinate. Are you okay? So even on most construction sites, there's a kind of regular grid based on which the whole project is being established. Are you okay? So now, why are we trying to do this conversion? Why don't we just keep the longitude and latitude if it's a coordinate system? If we can collect our data in longitude and latitude, the global positioning system, the GPS receivers are actually getting their coordinate in longitude and latitude. That can be related to around Earth. In fact, it's difficult for me. If you were in class, I'll be drawing something for you to appreciate some of these things. If you've forgotten what longitude and latitude, these are just lines moving from the North Pole to the South Pole, and then also parallel to the equator, which divides the Earth into two parts, the Northern Hemisphere and the Southern Hemisphere. Are you okay? Now, so at these geographical scales, then we can now say, okay, how do I... Yes, go ahead. Yes.
Oh, I thought you were using a Samsung Note.
What do you need?
Like what you are saying, you can write it on your screen. You can use your pen and write it on your screen.
And this is actually a PDF reader.
But you can see right do that. You use.
So where's the writer? Where's the pen?
There's a sign on your yeah. Okay.
This one.
Yeah, okay, that is different anyway. Okay.
So I think they don't have those tools. I mean, on the desktop, I think they have loads of tools, but over here, I hardly see.
If it's Note, you can still use it. You can still do that.
If it were Samsung Note, I could do that, isn't it?
Yeah.
Yes, but I think this is not. So I could also go to Note, but I don't know how good it will look like. Let me try it and see if it will be good enough. Let me see. So let me see if I can draw something here. There's a pen here that I can use. So, okay, so you can see that. Very good. That's a very good suggestion. God bless. Thank you so much. This is going to help. Okay, so you can see that your North Pole is somewhere here. And then your South Pole is here. Are you okay?
Yes.
And then you have the equator actually moving, going round and coming back again. Are you okay? So I can just do dash lines here. Are you all right? Okay, great. And then we go back, pick my blue mark, and I can do lines going from North Pole to South Pole. These are the longitudes. Are you okay?
Yeah.
And then I can have the latitudes go parallel to the equator. So this here is the equator. This line that actually divides the Earth into two, this is the equator. That black line going in the middle. Are you okay? Yeah. So now we have the Northern Hemisphere, this one, Northern Hem. Then we have, that's the top half. Then we have the Southern Hemisphere down here. Are you okay? Yeah. All right. Now, all the lines that actually go from east to west, okay, so east to west, these are called the latitudes. So these are latitudes. And the north-south, we have the, let me try and pull it down. Hold on. Okay. Yeah. So north-south, then we have the longitude and latitudes. Are you okay? Yeah. So this is how the Earth is. So can you imagine if you're actually doing a project around, say, this area? Okay. And then you've actually put it on a flat sheet of paper. It's looking funny, because the world isn't flat. So that's the argument. Now, the world isn't flat. So how can they be showing me a paper? You should be showing me something like a globe. So the globe is the best representation of the Earth, even though the Earth itself is not even perfectly spherical. Okay, it has its own issues. But because engineers, we are always trying to model and kind of come up with a mathematical formula, and everything we are doing is based on a formula of sorts. Then we need to find a way to relate, to model. Okay, so we want to relate the longitudes, which the longitudes, the mathematical symbol for it is actually, let me just try and do this. Yeah, okay, let me go down a bit. Lambda, this is a longitude, and we have phi. This is the latitude. Are you okay? So this is another way of saying x and y. Are you okay?
Yes.
We can relate to x and y. When we teach children in JSS and SHS, we're talking about x and y. We are telling them that flat, we never mention the fact that it's a lie. Are you okay? It's a lie. You don't start telling kids like world is round, you get confused. Even how many adults are able to appreciate that? Are you okay? So because when you walk around, you feel it's flat anyway. Okay. So the mathematical translation or transformation from longitudes to x and y is map projection. So I think I'm done for the day. I think we can say goodbye and go. This is it. It's mathematics. It's not a very nice fairy tale that we are telling for you to feel so good. Are you okay? And get the goosebumps. It's just a formula to transform everything that we have on the round earth to the flat surface. So as you can see over here, you can see that everything I've said over there now, on the flat, on this map here, or on this map, now we are having x, longitudes are x. You see, not that alone, you have to think about it for like some days and then come to appreciate it. Longitudes are not y, they are x. Longitudes are actually y. Okay, so as an engineer, you need to do that. You need to appreciate these values. You think longitudes are going from top to down, so it should be y, but actually they are rather x. They are measuring how far you are moving from left to right, and that is x. And then your latitudes are really telling you how high up you are, how close you are towards the North Pole or the South Pole. And so we need to appreciate this data. All your GPS receivers are receiving longitudes and latitudes. You are holding it to your hand right there. They are a confirmation that you are not working on something flat once you are dealing with your longitude and your latitude. Okay? So that is that. We need to do this transformation because some of the data or most data may not be in the same system, the same coordinate system. And so there's a need to transform. Why do you need to transform? So that you can overlay. Remember we talked about overlay and map layers. You can never add overlay two layers unless they are in the same coordinate system. In other words, even in AutoCAD, if the values you are bringing in for your site, if the coordinates aren't right from your Excel to your AutoCAD, when it comes, it will be lying somewhere else and it will not agree with your project site and everything that you are doing in there. Are you okay? So it's the very reason why we do the projection is to allow us to actually integrate data in GIS. So it's for this integration. So here you see how the one topic is linking with a topic that we've dealt with already, that we can actually stack different layers, but then we can only stack them together. In fact, I even told you when I was having that lecture, that reminded me when we get here, that without having data in the same coordinate system, when you overlay it wouldn't even make sense. Are you okay? So you'll be having the pipeline project and you want to bring in the routes, and then the routes are lying in northern Ghana, and then your pipeline is lying in the sea. It won't work. Are you okay? So it's very important for us to appreciate the justification for map projections. Are you okay? So yeah, I think it's all been said over here. We need to do a transformation. Are you okay? From 3D to 2D, more or less, but it's not really like the way you look at it. It's just, the formulas actually been, they've been derived already, yeah? And then all you need to do is apply them. These formulas have been implemented. If it's a web application, it's already been implemented, written in JavaScript or something like that. If it's a phone, then Android, Java, yeah, has been used to write it. You don't have to worry about it. But yes, I need to know that this is actually, an important concept. Otherwise, you get frustrated. Are you okay? All right. So we here the second point bullet is saying that it's a convenient surface to deal with as opposed to the three-dimensional surface. What he's saying is that we would like to work with 2D. Engineers would like to work with 2D instead of to work with a 3D surface. In fact, it does make a lot of sense to work on a flat surface than to work on a round surface. It's just convenient. The keyword is convenient, so that we can do measurements. We can also visualize. Are you okay? Data. Are you okay? Because look at the globe. The globe is actually a map, but it's really 3D and it's not convenient. So people put the globe in their office and they watch it like a toy. Nobody, you hardly see people actually working on a globe. And most of the movies that you watch, the war movies in the 1940s and 19 whatever, when they were actually like bombing countries, were bombing countries and all that. You realize that they were actually using flat maps. Nobody has actually considered using a globe or 3D surface representation of the Earth. Okay, so this mathematical transformation is what we are calling map projection. It's mathematical transformation from longitudes, okay, and latitudes to X and Y. That is what we are calling map projection. But the concept can be explained. So you should know how to answer the question. Are you okay? At the end of the day, it is a mathematical transformation. All right, great. So let's move on. And so what? I'm sure someone will be asking. So I think some of the things I have talked about being said again. Are you okay? Yeah. When you want to actually understand map projection, always think about taking a round ball and then you shine light through the ball. And then you actually point the whole thing, the light source towards the wall. Are you okay? So you're holding something like a torchlight. You have a transparent ball. Are you okay? And then, but then meanwhile, you've drawn something on the transparent ball, and then you actually shine the light through it. It will push everything that you've drawn on the ball onto the wall. That is how it is with map projections. Are you okay? All right. So that is why we call it a projection. It's just like, projection, as we will say, light be projecting something, pushing it on a wall. Okay. So that is the formula you see that you started writing some functions over there. So map projection from longitude to XY, we make use of the latitude, longitude, and then we'll get the X. And then to get a Y2, we make use of the latitude and the longitude. So that's the phi and the lambda I talked about. Are you okay? And then you can also have it properly written. Very nice. You've all done some integration before. So you can do the integration and are you okay? And then arrive at a very nice formula looking like that. So here you can see that there's lambda up there. Are you okay? Translating directly to the X, because longitude, I told you the longitude is the X. And then we can have Y being a function of the latitude. And then we've got a constant pi. This is natural log, and then tangent comes in there. So this is the maths of map projection. You can also do the reverse format or the inverse transformation, where you want to get the longitude from the X and Y. It should be possible. But you should have known the kind of formula that was used up here. Okay, then you know how to reverse it down here. So here, X is being given to longitude, and then phi is not really as simple as this. This is just for for you to appreciate that this is what goes into it, transforming data which is on 3D to data which is on actually 2D. Are you okay? This is what we go through. This is what the computer does. This is what the software does when the transformation is done. So map projection, when you want to use, one of the things that you need to do is to quickly shade what the in fact you'll be wasting your time. A lot of things that you do won't work. Are you okay? So yeah, I think our meeting will end in 10 minutes. When it ends, please kindly go and pick the same link that we used. Is that okay? All right. So now the transformation, when you actually transform it, you're going to have issues. You're going to have some problems. Some of the shapes aren't going to remain the same. Are you okay? Some of the directions too, you're going to miss it. So you appreciate what it takes to actually fly an aeroplane from one airport to the other. After this lecture, you appreciate it more. Are you okay? You'll be wondering, okay, if the world is even round and I'm taking off of it, would I be going in the as a kind of bent, curved line, or I'm going to go in a state. So some of these questions will keep coming in your mind, and it will tell you the importance, okay, of applying mathematics to some of the things that we do, okay, in real life. So we need to appreciate that there will be challenges in terms of we can have area not being preserved. Sometimes you can have the direction not being preserved. In other words, you think you are going in this direction, but you are going in the other direction because you are using a flat map, and what you're actually traveling on is a curved surface. It's a spherical surface. So there's a lie in there, and you are paying a price for it. Okay. So there are so many projects that people came out with. In fact, in the past, there have been a lot of accidents with ships trying to move, navigate. Napoleon Bonaparte, whoever in history, people are traveling, their ships are actually running into rocks because they thought they were going in this direction and they're going in the other direction. It's been a challenge. Are you okay? And so there's been research and effort has been put in to find out what's the best way to do it so that we don't get it wrong. Are you okay? So many projections have been developed. Okay, and the whole idea is to accurately represent a particular, map element, the area of the Earth. Should we preserve the area or preserve maybe the area? Okay, or the direction. Should preserve area or direction. We have equal area maps and etc. Equivalent maps or different types of maps. I mean, depending on what you want to use. But I'm not going deeper into all that. But I want you to appreciate that we need to, preserve some part of it. So now, let's look at here. This one, what are we seeing in this slide? Data sources for map come in various projections. I think I've talked about this. So the map projection is synonymous with the coordinate system. So when you get a data set, when I give you a data set, it should, as part of the metadata, you should also have the map projection information in there, telling you that this map, the data that I have was even collected with this GPS and the map projection is so and so that you know what to do, what transformation to take it through. Most GIS software have the different projection that can allow you to transform from one data, projection, map projection to the other. Are you okay? All right. So the one that the GPS is giving us is the WGS84. So they have names. Can you imagine that? Coordinate systems have names. What we learn in, let me just say, primary school and coming up secondary school, college, is they are all actually Cartesian coordinates, X and Y. So the math teacher will be drawing a whole of quadratic, equation, plot a curve for it, all that way, that in that format. Okay, so I think there's something missing on my slide. I'm supposed to teach you the different types, but hey, I didn't check this one out. Guys, I think, let me go back to the notepad and I'll talk you through that one. There are 3 different classes of projection. So let's look at that. Okay, different class, because there are actually a lot of people who have actually thought about it, that okay, how then would you represent something round on something flat? Okay, how would I represent this on that? How would I get that transformation from longitude and latitude? So remember, this is lambda and then phi to x and y. Okay, someone came out with the idea, oh, it's not a problem. Take the round Earth. Okay, someone said, and then put a flat surface on it. And then project everything on the round Earth onto the flat surface. By so doing, of course, you are projecting the longitude and latitude onto this one. Okay, so now this becomes the map, flat. Now, okay, of course, mathematically, we are saying this is a globe. Okay. All right, so now he said, let's call this one the planar projection. So this is a class of projection. We call it a class projection. Okay, so calling it planar or using a flat surface, another name for it is the planar. Another name for it is, so either it's planar or it's azimuthal. Or we can also call it stereographic. stereographic projection. Are you okay? So brilliant idea, isn't it? So the North Pole is up here. Let me get the color. Here's my colors. Okay, great. So my North Pole is up here. Always remember that. And my South Pole, the South Africans, they are here. Yeah.
Yeah.
Okay. So someone came out with this and said, people were like, brilliant. How do you do this? So a whole lot of formulas were written. The whole idea to transform lambda and then phi into x and then y, which is what my projection is all about. Okay, and then the names started coming up: azimuthal, stereographic, and someone said, hey, hold on. This may work for the poles, but may not work for Africa and for Brazil, Southern America. Okay, may not work for Australia. I am coming out with something else. Someone said, okay, then let's try this one. You have the Earth as a round surface, but this time around, fits a cylinder onto it. Hey, our 10 minutes, I'm sure right now we got 2 seconds, right?
1 minute.
You got 1 minute, okay. Hey, class, but you were not going to tell me. Hey, I thought we were friends.